So let's go through the new dot points now, the following dot points. So 2.3.1, conduct practical investigations to determine the concentrations of solutions and investigate the different ways in which concentrations are measured. 2.3.3, conduct an investigation to make a standard solution and perform a dilution. So the thing with these are practical dot points. So they're conducted more in depth at school, and they're basically applications of the content that we've already just covered just then. So in these like dot points, you'll investigate concentrations and how they're measured, dilutions, standard solutions, etc. So these are practical dot points, so not too much that we can cover within our 2-hour lecture, but you will cover them more in depth at school. And if you're solid, or if you've got a solid understanding of the content that we've covered so far, then you should fare pretty well when you encounter these practical dot points. So with that said, now let's go on to the process of dilution, calculating dilutions, right? So you can see with this image over here, which one is more diluted? Well, this one is more diluted than this one, because you can see the shape, or like the intensity of the color, is decreasing as it goes on. So that kind of shows the process of dilution. So standard solutions now. Standard solutions are solutions with a known concentration of a substance. So a known weight of solute is dissolved to make a volume, and they're used to determine concentrations of other substance through a process called volumetric analysis. So we're finding the volume of the substance to calculate other properties of it. So that's what volumetric analysis looks like, including a process called titration, which we'll learn more in the HSC course. So you will learn this more in module 6 and module 8 in your HSC course, titrations. So what it looks like, how to calculate standard solutions, what it looks like is basically in step A, you accurately weigh out a mass of sodium carbonate, which is the primary standard in this example. So you weigh out a mass with using that mass, we can calculate the amount of moles of sodium carbonate that we have. So we'll measure out like a mass that would give us, around 1 mole of sodium carbonate, for example. So we'd accurately weigh out that specific mass using a very sensitive scale. Then we'll transfer that sodium carbonate, Na2CO3, to a volumetric flask. So that's step B. So we're transferring into a volumetric flask. And then why a volumetric flask instead of a beaker? Well, the markings on a volumetric flask are a lot more accurate than the markings on a beaker. So there's a lot less percentage error in a volumetric flask. And then what do we do? And then we ensure the complete transfer of Na2CO3 by then washing this thing with water, right? So we're transferring the Na2CO3 through a volumetric flask. Then we're adding in the water that we add it to a volumetric flask, so the beaker. And then what we do is, because there might be still some particles left over in our beaker, what we do is we thoroughly rinse out that beaker with deionized water, making sure everything coming out of that beaker flows directly into the volumetric flask to ensure complete transfer of our sodium carbonate. And then we fill it up to the line. So we dissolve the Na2CO3 in the amount of water that we have, and then we make up the water to the solution. So the calibrated mark is over here. And we've inputted this much water into our solution, into our beaker. So now we can fill it up to our required solution, or our required amount of water needed, ensuring that the sodium carbonate is dissolved within our solution. And after all these processes are done, we now have a known concentration of sodium carbonate, because we know the amount of moles that we used, and we know the amount of water that fills up to this calibration mark. So we know the concentration of the standard solution, basically. That's basically how we find a standard solution. Now we go into the next inquiry question, which is gas law. So the next inquiry question is, how does the ideal gas law relate to all other gas laws? So in this inquiry question, or in this section of the module, students, they conduct investigations and solve problems to determine the relationship between the ideal gas law and Gay-Lussac's law, which relates temperature, Boyle's law, Charles' law, and Avogadro's law. So we have 4 different laws and the ideal gas law, and then we find the relationship between all of them. So let's go through. Let's go through first the Kelvin temperature scale. So you might have heard of the term absolute zero. Absolute zero is like basically the lowest temperature that you can go through. It's a point where molecular energy is at a minimum. So at this point, so heat is defined by how much a molecule vibrates, right? How much energy stored within that molecule can dictate heat, right? So when there's zero energy within that molecule, so the kinetic energy of that molecule is zero, then we're at absolute zero, which is the beginning of the Kelvin temperature scale. So that's a 0 degrees Kelvin. And 0 degrees Kelvin is also minus 273.15 degrees on the Celsius temperature scale. So then so temperature in Kelvin then is equal to temperature in degrees Celsius plus 273.15. So 10 degrees Kelvin is equal to 10 degrees Celsius is equal to 274.15 degrees Kelvin. So that's how we convert between the two of them. Similarly, 10 degrees Kelvin is equal to negative 263.15 degrees Celsius. So that's how we convert between the two. All right. So so the boiling point of water is 100 degrees Celsius, or 100 plus 273.15, so 373.15 degrees Kelvin. So that's how we would convert between the two of them. All right, now let's look at the gas laws. So we have 5 different gas laws, and we have the universal gas law over here. So we have we have P1 V1 is equal to P2 V2, V1 over N1 is equal to V2 over N2, V1 over T1 is equal to V2 over T2, P1 over T1 is equal to P2 over T2, and P1 V1 over T1 is equal to P2 V2 over T2. So we have 5 different things, and we have the universal gas law over here. PV is equal to nRT, R is a constant, T is temperature, N is moles, V is equal to volume, and P is equal to pressure. So that's how you break down that equation. So let's look at the ideal gases. So ideal gases are hypothetical gases whose molecules occupy negligible space. So they have no interactions and they obey the gas laws exactly. So pressure, which is measured in kilopascals, volume in liters, N, which is the number of moles, R is the universal gas constant, which is 8.31 joules per mole per Kelvin. And then we also have temperature, which is measured in Kelvin, not Celsius, Kelvin. So in science, we use Kelvin, not Celsius, because that's just the SI unit for temperature. So always make sure when they give you a value for temperature to convert it into Kelvin. Okay, so now we go through Boyle's law. So Boyle's law states that for a given massive gas at a constant temperature, its volume is inversely proportional to pressure. So the Boyle's law basically looks at the relationship between pressure and volume. So if you want to memorize it, Boyle's law is boiling, so pressure and volume basically. So we have high temperature, therefore so if we're boiling water, that means we have high temperature, and so temperature is kept constant. So what is changing? Pressure and volume. So P1 V1 is equal to P2 V2. So if pressure 1 increases and volume and temperature is kept the same, then pressure 2 has to also increase, etc. If pressure 1 increases, so P1 increases, but P2 is kept the same, then V2 has to increase, so the volume has to increase. So that's just how that works. Okay, so now let's look at Charles' law. So Charles' law states that the volume of a fixed amount of gas held at a constant temperature is proportional to its absolute temperature measured in Kelvin. So this is the relationship between volume and temperature. So V1 over T1 is equal to V2 over T2. So Charles is Prince Charles, so royal family member, undergoes a lot of pressure. Low-key kind of a trek to memorize this entire thing, but yeah, if it helps you to memorize it in that form of like story association, then go for it. So V1 over T1 is equal to V2 over T2. So V1 and V2 are volumes of gases. T1 and T2 are the temperatures of these gases in Kelvin. Now let's go through Guy-Lussac's law. So Guy-Lussac's law states that the pressure of a fixed amount of gas at a fixed volume is directly proportional to its temperature. So this one is the relationship between temperature and pressure. So P1 over T1 is equal to P2 over T2. So P1 and P2 are the pressure of the gases, and T1 and T2 are the temperature of the gases. And for Guy-Lussac's law to be observed, the volume of both systems must be kept constant. All right, so now let's look at the combined gas law. So the combined gas law is when you combine all of these. So it's a relationship between Guy-Lussac's law, Boyle's law, and Charles' law. So P1 V1 over T1 is equal to P2 V2 over T2. The pressure of all the gases, the temperature of the gases, and the volume of all the gases, and the relationship between all three of them. So we also have Avogadro's law now. So we know Avogadro's law, so we think about, okay, probably it's relating something to do with moles. So Avogadro's law states that equal volumes of all gases at the same temperature and pressure have the same number of molecules within them, which kind of makes sense, right? As long as the pressure and temperature doesn't change and the volume is kept constant, then the same amount of particles have to occupy the same place, right? So this is the relationship between the volume of a gas and the amount of substances of gases within that substance. So V1 over N1 is equal to V2 over N2. V1 and V2 are the volumes of gases, N1 and N2 are the amount of the particles of gases present, or the number of particles of gases present. So, quick summary of gas laws now. So we have Boyle's law, which is P1 V1 is equal to P2 V2. So at a constant temperature T, as pressure increases, volume decreases. Charles' law, which is V1 over T1 is equal to V2 over T2. So at a constant P, as volume increases, temperature also increases. Now we have Guy-Lussac's law. So P1 over T1 is equal to P2 over T2. So at a constant V, as pressure increases, temperature also increases. Then we have the combined gas law, which is P1 V1 over T1, which is equal to P2 V2 over T2. So it's obtained by combining Boyle's law, Charles' law, and Guy-Lussac's law. And we also have the ideal gas law, which is PV is equal to nRT, which is like a further combination of everything, all the variables that we have over here. So this is probably a good thing to keep in mind. This slide over here, it's a good summary of all the gas laws. So another quick summary. So for a given amount of gas at a constant temperature, the volume of gas varies inversely with pressure. That is Boyle's law. Charles' law states that the volume of a fixed amount of gas is directly proportional to its Kelvin temperature if the pressure is kept constant. Guy-Lussac's law states that the pressure of a gas is directly proportional to the Kelvin temperature of it if the volume and amount of gas is kept constant. The combined gas law now states it combines Boyle's, Charles, and temperature pressure relationship into one equation. So each of these laws can be derived from this law. Avogadro's law now states the pressure of a gas is directly proportional to the number of moles if the volume and temperature is kept constant. And the ideal gas law, which relates pressure, temperature, volume, and moles through the gas constant, R. So this gas constant, you don't have to worry too much about it. They'll give you the gas constant in your data sheet. It should be in the very first page. All right, we'll get to a final question now. So at what temperature in degrees Celsius does 48.5 grams of CO2 occupy 4.56 liters and have a pressure of 2.5 atmospheres? So to solve this, we use the amount of moles that we have. 48.5 grams of CO2 is equal to 1.10 moles of CO2. Volume is 4.56 liters. Pressure is 2.5 atmospheres. Temperatures is what we're trying to find temperatures, right? So R is equal to 0.0821. PV over NR is equal to T. We rearrange this ideal gas law, so we divided both sides by NR to isolate T. So T is equal to 2.5 times 4.56, all divided by 1.10, which is the number of moles, times 0.0821, which is R, to get a temperature of 126, not degrees, Kelvin. So in reality, this temperature would probably be minus degrees in Celsius, but in positive degrees in Kelvin. So 126 degrees Kelvin. That's how we would use the ideal gas law to solve a question like this. All right, so also a disclaimer, sometimes they might not give you like moles, etc. So if they don't give you moles and stuff, then they're asking you guys to use one of the other four laws. They're asking you guys to use one of these, Boyle's, Charles, Guy-Lussac's, or combined gas laws. If they don't give you guys a variable, you need to be pretty confident with all of the gas laws in case they don't give you all the variables. So you can't use ideal gas law in some cases. But in most cases, you should be able to use ideal gas law. And another important thing is you should be able to define all of these. So with that said,